Hello everyone, today let's take a look at Quantipus number 5, a classic symmetry question where we have 100 airline passengers waiting to board a 100-passenger airplane. So everyone holds a ticket assigning them to one of the seats, but the first passenger is drunk and chooses a seat at random. Now all the other passengers will sit in their assigned seat unless it's already occupied, and in that case they're going to sit in an unoccupied seat at random. So you're the last person aboard. What is the probability you end up in your assigned seat? Okay, so first of all, let's just do a run through to see what's happening. Basically, these all represent the seat numbers, so seat 1, 2, 3, 4, all the way up to 100. And let's just say, to make it easier to understand, it doesn't change the probability at all, but let's just say that the drunk person has seat 1, and then the second person in line is seat 2, and the third person in line is seat 3, just to make it a little bit easier. So that means that we are going to have seat 100 because we are the last to board. Okay, so we have 100 empty seats, and the first passenger to board is the drunk person, right? So they're going to choose a seat at random. So they could choose any of these seats with equal probability. So let's say that they choose seat 3. So even though this drunk person's assigned seat was seat 1, they ended up sitting in seat 3, right? So now we continue. The next person to board is person number 2, and all of the other passengers will sit in their assigned seat if it's available. So person 2 sees that his seat's available, and he's going to go sit in it. Okay, but now it's person 3's turn to board, and when they do so, they're going to see that seat 3 is taken by the drunk guy, and in that case, they're going to sit in an unoccupied seat at random now. So person 3 is kind of, in a sense, becoming the new drunk person, just with less seats to choose from, right? So for instance, person 3 now is going to choose any seat at random. They could choose, for instance, like 79. Let's say person 3 sits here, and now what's going to happen? Well, now person 4 boards, their seat's open, so they're going to sit in it. Everyone up to seat number 79 is going to board into their correct seat until it gets to person 79, who now sees that person 3 is in their seat. So now again, person 79 has kind of become the new drunk person, and they again will sit in an unoccupied seat at random. So now let's say that person 79 sits in seat 100 just randomly, right? They're just choosing from the remaining available seats. Well, that was your seat, so in this case, you're not going to be able to sit in your seat, right? So now let's actually solve the problem. What is the probability that you end up in your assigned seat, right? So let's define this event A to be the event that you sit in your seat. So now what is the probability of A? Okay, so let's reset and kind of just think about this seat by seat. Okay, so we know for the first guy, who's the drunk guy, right? He could sit in any of 100 seats. So our probability space is going to look something like this. It's going to be broken up into 100 tiny boxes where each one represents the probability of the drunk guy sitting in that specific seat. So again, it might look something like this. I'm not going to draw the whole thing out, but we know when our sample space is partitioned like this, we can use the law of total probability, and let's condition on where the drunk guy sits. Okay, so all this is saying, we've seen this before, is that the probability of A is just equal to the probability of A, given that the drunk guy sits in this seat, weighted by the probability mass of him sitting in that seat. Okay, so let's just go through seat by seat and see what the probability of winning is when he sits in every single seat. So let's start off with when he sits in seat number 1. And now notice that this is kind of a special case in the sense that when the drunk person sits in seat number 1, they're actually sitting in their assigned seat. So he's not taking the seat of any of the non-drunk passengers, so they're all going to be able to sit in their assigned seat, including us. So when he sits in seat 1, the probability of us sitting in our assigned seat, given that he sat in seat number 1, is equal to 100%, right? And we weight that by the probability of him sitting in seat 1, which was 1 on 100, obviously, is equally likely to sit in any seat. Okay, so now let's look at the other really simple cases. That's when the drunk guy sits in seat number 100, which is your seat. So when he does that with 1 out of 100 probability, what are your odds of sitting in your own assigned seat? Well, obviously 0 because he's sitting in it, right? So 0. Okay, our two simple cases. Now let's come back and look at the situation where he sits in seat number 2. Well, in this case, after he does that, person number 2 is going to come along, see that this guy's sitting in his seat, and now he's going to effectively become the new drunk person, right? So now person 2 is going to choose one of the remaining 99 seats to sit in at random. So now can you notice the recurrence relation? We're effectively solving the exact same problem that we were originally, but just with one less seat. Okay, just to make the recurrence relation easier to understand, I'm going to call P of A f of 100 now. Okay, so I just move this down here. Now let's get back to this case. So the drunk guy is going to sit in seat 2 with 1 out of 100 probability, and then when he does so, we're left in the situation where the second guy becomes the new drunk guy with 99 seats remaining. So what's my probability of sitting in my assigned seat now? Well, let's call it f of 99. Now let's look at the case where the drunk guy sits in seat number 3. Okay, so now person 2 is going to be able to sit in their assigned seat, but now person 3 comes along and they see that the drunk guy is sitting in their seat, so now they become the new drunk guy. So this also had a 1 out of 100 chance of occurring, and when it does, we have an f of 98 chance of sitting in our assigned seat. Now you can pretty clearly see the pattern. This is just going to keep on going, right? So you understand what's going on at this point. We have f of 100 is equal to 1 out of 100 plus 1 out of 100 times 0, which is just going to be 0. And then we're going to end up summing 1 out of 100. We can pull a common factor times the sum of all of these f's that keep on going. So it's going to be f of some iterator, let's say. So all these are going to be f of 99 plus f of 98 plus f of 97 all the way down to, well, let's figure out actually what it goes down to. If the drunk person originally sat in seat number 99, well, then what would happen? Well, in this case, the people numbered 2 through 98 are going to end up sitting in their correct seats, but then when person number 99 comes on board, they're going to see their seats already taken, and they're going to choose randomly between seat 1 and seat 100. So the drunk person's choosing between 2 seats, so we'll call that 2. So our iterator is going to go from 2 all the way up to 99, right? Okay, so now we have our equation, but we need to figure out what's going on with this recurrence relation. So how do we start? Well, do you think it's easier to start with I equals 2 or I equals 99, right? Obviously, it's going to be I equals 2. We're going to start from our base case, and let's look at f of 2. Okay, so in this situation, we have 2 seats on the airplane, right? One for me and one for the drunk guy. So what are my odds of sitting in the correct seat? Well, he has a 1/2 chance of choosing his seat and a 1/2 chance of choosing my seat. And if he chooses his seat, then I'll sit in my correct seat. And if he chooses my seat, well, then I won't, obviously. So my odds are 1/2 here. Okay, that was simple. Now let's look at f of 3 and work our way up as we do with all recurrence relations. So now I have 3 seats for 3 people, and the drunk guy is going to go first. So he has a 1/3 chance of sitting in his assigned seat, in which case I will end up in my seat 100% of the time. Now he has a 1/3 chance of sitting in the middle, which happens with 1/3 probability as well. So what's going to happen now? Well, now the second guy is going to come along and see this guy sitting in his assigned seat. So what's he going to do? He's going to become the new drunk guy, and he's going to sit here with 1/2 probability and here with 1/2 probability. So what are the odds of me sitting in the correct seat now? Well, it's going to be f of 2, right? This is the same situation that we just did, and we calculated f of 2 is 1/2. Now finally, if the drunk guy sits here, which is my seat, I'm not going to be able to sit in my seat, obviously. So plus 1/3 times 0. So what's my final answer? 1/3 plus 1/3 times f of 2, which we know is 1/2. So 1/3 plus 1/6, and what do you know? That's also 1/2. All right, now let's do a few more. What's f of 4? So drunk guy sits here with 1/4 probability. In that case, I'm going to wind up in my seat 100% of the time. If he sits in the second seat, well then now the second person becomes the new drunk guy with 3 seats to choose from. So 1/4 chance of f3 happening, which again, we already calculated. If he sits here, person number 2 is going to sit in their correct seat, and now person number 3 will become the drunk guy with 2 seats remaining. So 1/4 chance of f2 happening, which we also already calculated. And finally, if he sits in our seat originally, well then we're going to have a 0% chance, again, obviously. So 1/4 times 0. So now you kind of notice what's happening, right? These are all going to be 1/2. We already calculated them, and when we sum this up, we're going to get 1/2 again. So can you see what's happening, right? In our special cases, right, when he either chooses the seat that he's assigned or he chooses our seat, well, in those cases, we're going to sit in our assigned seat half the time. And when one of our special events doesn't happen, well, then we're kind of just kicking the bucket down the road, and we're going to go to a lower case. And in these lower cases, like we've seen, we're going to have the same thing, right? If we have a special event, then we're going to sit in our assigned seat with half probability. Otherwise, we're going to kick it down the road until we can't anymore, and we get to f of 2. When we get to f of 2, it's trivial, right? The drunk person will sit in either seat with 50% probability. So either we kick the bucket down the road long enough to where it's trivial and we actually have 50% probability, or of the cases that actually decide the outcome, we have 50% probability among them, right? Here and here. So you can see how this is just going to keep continuing, right? F of 4 is going to be 1/2, f of 5 is going to be 1/2, f of 6 is going to be 1/2. So let's come back and look at f of 100, which was our original question. So all these f sub i's now we know are equal to 1/2. So when we sum up 98 of them, we're going to get 98 divided by 2, which is 49. We take that on 100. We have 49 on 100, and then we add on this 1 out of 100. And what do you know? That is 50%. Okay, so this is our final answer right here. Okay, real quick bonus question. Let's actually prove this by induction. So for n greater than or equal to 2, prove f of n is equal to 1/2, where f of n is the probability that the last passenger sits in their assigned seat on an n-passenger flight with one drunk person at the front, right? And this will be pretty simple to do. If you watch the whole video, we've basically already done it, but let's just formalize it. So we know in a proof by induction, we need to start the base case, so f of 2. So this is super trivial. They have a 1/2 chance of sitting in their own seat, in which case you have a 100% chance of sitting in your seat. And if they sit in your seat with 1/2 chance, then you have a 0% chance of sitting in your seat. and this equals 1/2. So now all we have to do is the inductive step. So again, we know how to do this. Assume that f of k is equal to 1/2 for all k between 2 and n, and now we need to show f of n is equal to 1/2. And again, I feel like we've already shown this, but f of n is equal to 1 out of n times the probability that they sit in their own seat, in which case you will sit in your seat. So 1 and plus 1 out of n times the probability they sit in your seat, in which case you won't sit in your seat. Now we add on the probabilities for all the other seats, which we already know is going to be 1 on n times the sum. Let's take k going from 2 all the way up to n minus 1 of f of k. Now would you look at how easy that is, right? K is going from 2 to n minus 1. What do we know? Well, we know that f of k is equal to 1/2 for all k between 2 and n minus 1, right? Because this is not inclusive. So now since this term is 0 and f of k is equal to 1/2, well, we're assuming in our inductive step, well, then we can rewrite it like this, obviously. So now we're summing up a constant from 2 to n minus 1, so n minus 2 total times. So this entire equation is going to be 1 on n plus 1 on n times n minus 2 on 2. Now this is just going to be equal to 1 plus n minus 2 on 2, all of that divided by n. Now this 1 in the numerator is equal to 2 on 2, so we're going to end up in the numerator with n minus 2 plus 2 on 2, and in the denominator just n still. So these 2's up here are going to cancel, and we're going to get n divided by 2, all of that divided by n. And this is obviously equal to 1/2. So there we've showed by induction that every f of n is equal to 1/2. All right, sorry for that digression, but back to the original problem. Basically, we know that the person who decides the outcome is the person who either sits in seat 1 or seat 100, and all it boils down to is that they have equal probability in every situation to choose between seat 1 and seat 100, right?